This is our first video lecture in our contaminant transport course, our 1 credit course on contamination in groundwater. So the first module, so the first few lectures will be dedicated in introducing transport equations, so the advection dispersion equation essentially. And in this very first video, I reviewed the concept of diffusion and concentration gradients and how things move by diffusion transport, before then adding notions of advection and dispersion in the following few lectures. So first a question, in a gas or in a liquid, right, which one is faster? So is diffusion faster in a gas or in a liquid? And intuitively, right, we all know that liquids are denser than gas, so diffusion is slower. So we already see that viscosity and slash density, but viscosity essentially, have an influence on the diffusion of particles in fluids. So the diffusion of water in water gas, right, water vapor in air is 0.2 square centimeters per second, and the diffusion of water in water, so liquid in liquid, is 2 e minus 5 square centimeters per second. So we can see that, liquid in liquid diffuses much slower than gas in gas, which makes sense. Now, where is the diffusion process a primary transport mechanism? And the answer is right there, anything small. And so again, diffusion is so slow, basically, that it's only efficient at short distances. So in real life examples are, the classic neurons, neurotransmitters in the brain, because it's really just that tiny gap between synapses, or between brain cells, between neurons. So at this scale, it's very efficient to release some neurotransmitter, and then just by diffusion, right, it's transported to the other side, to the other cell, and then triggers, reaction in that cell. Now, if we look at mass transport at the scale of, the entire body, so let's say from your heart to your lungs, or from your lungs to your organs, let's say you need oxygen, to run, so let's say your muscles in your legs, right, are a meter away, then diffusion is not an efficient transport mechanism, and there's a pump, which is the heart, right, that, helps basically transport between further, organs that are further away. And again, we'll talk about this a little more when we deal with advection. Okay, so again, you can calculate, how long does it take to travel, between two synapses, or the synaptic gap, or how long does it take to travel from, let's say, your lung to your brain, right, to oxygenate your brain. And the time scale here, so what's important here is the time scale, and I'm sorry, my pen is not working, but so if the synaptic gap is a micron, right, we can find a time scale that is, the length squared divided by the diffusion coefficient. Remember, the diffusion coefficient is a length squared per time, right? The units, so centimeters squared per second, meters squares per second, so on and so forth. So meters squares per second, we want a time scale out of it, right? So 1 over meter squares per second is second per meter squared. And now to eliminate the meter squared, you just take the relevant scale, so in this case 1 micron from the synaptic gap, square that, and then find the answer, like it says here, right? So again, for 1 micron, so it's 1 e minus 6 meters times 1 e minus 6, again, length squared, divided by 2 e minus 9. So this is the diffusion of water in water, but in squared meters per second as opposed to centimeters squared. So this is a good number to remember, actually. And then you can see that the answer to move, through that micron distance is about 0.5 milliseconds. So 0.5 milliseconds is very fast, right? So it's very, very fast. Now, if we do the same calculation from your lungs to your brain, and let's assume it's a meter, obviously it's less than that, but just order, 1 meter, or let's say if it was from your lungs to your muscles in your legs, right? Same story. So it's 1 meter. Let's say to go 1 meter by diffusion, again, do the same calculation and find that it takes a year and a half, right? So a year and a half obviously is not a transport mechanism that is efficient enough, right, to to work, basically. Okay, so that was just a quick review on diffusion timescales, notions of diffusion and concentration gradients, moving things from one place to another. So like we've seen, it's very efficient at short distances, not very efficient at large distances. And in the next lecture, I will talk more specifically about the diffusion equation and how we derive it. All right, thank you.